So we've been talking a lot about magnetic fields and changing magnetic fields. And we've already covered how Faraday's law is incredibly important because it's responsible for all generators. So all of that electricity, or virtually all the electricity that comes out of the outlet, is generated because of Faraday's law. Well, magnetic fields show up in a lot of devices in other ways. Specifically, there's another electrical device called an inductor. So an inductor is just a coil or a solenoid. And I don't think I've shown you any of these, but here are two pre-manufactured. Now these are large scale, but this is cotton covered wire wound nicely and tightly. This is painted wire, because if it wasn't painted, then the current would just go straight through. But it's painted, so it's forced to go. So this is like a miniature slinky, basically. This one, the same thing, it's just paper, cloth covered. So we have two coils here. This is actually from, you may be able to tell, a rather large scale electrical device. This is actually a demonstration thing. But in your cell phone, there are inductors. There are little tiny coils. So a solenoid, you know, makes a B field. The magnetic field of a solenoid is given by mu naught n, little n, times I. So if there's a coil and there's a magnetic field, that means we can calculate a magnetic flux, B times A. So we're going to do mu naught n I times area, but then a solenoid has a lot of coils, so we need to multiply by the number of coils. And remember, number of coils we've used for capital N. So we have number of coils and we have little n, which is number of coils per unit length. So we can rewrite this as n times mu naught n over L, and I'm writing it curly for a reason, I times A. So we finally come up with the flux through a solenoid is mu naught big N squared I A, all divided by the length. So if you double the number of coils on a solenoid, you actually quadruple the magnetic flux through there. If you make it longer, you have less flux. That makes sense from what we did before with the magnetic field, because the magnetic field's weaker. But doubling the number of coils in the same length has a quadrupling effect, because you both have more coils to do flux, and you have more coils in that same length. So the two different places it does it. Now, that's all well and good, but what gets interesting is if we change this flux. So, oh no, I'm sorry, before we do that, we're going to define this term called inductance. So inductance, for again reasons no one knows, is defined, one, it's the letter L, but it is defined as the flux divided by the current needed to produce that flux. So if we go back in here, L for a solenoid would be this thing divided by I. Well, there's only one I, so we just get mu naught n squared A over L. This is why I wrote the curly L. We have two L's. This L is inductance. This L is length. I even wrote the curly L there. So it's important to keep those separate. Notice that this inductance, this new circuit element, only depends on physical quantities of how you built it. How many coils did you wind on this? How long is this coil? What's the cross-sectional area? So I know this from how I built it, not how I connected in the circuit, how I built it. These are only physical characteristics of how it's built. So of building it. I want to remind you of two similar ideas. With capacitors, if you want to build a capacitor, you choose a dielectric, you have this constant. The bigger the area, the bigger the capacitance, the closer together the plates, the bigger the capacitance. We also have for resistors. You choose a material with resistivity. The longer you make it, the more resistance. The bigger the cross-sectional area, the smaller the resistance. So all three of now these circuit elements, we choose how to build, and it has nothing to do with what circuit we're eventually going to use it in. Then we're going to put them in circuits. Oh, except I've got to tell you the unit. The unit of inductance is called the Henry. and it is equal to a Weber divided by an amp from this definition. And you could put your numbers in here with meters and counting and the funky units of mu naught, and you would get the same result. But now, as I was about to say earlier, if we've got a flux, what we really want to do is change that flux in order to generate an EMF using Faraday's law. Faraday's law, and that's right at the bottom of the paper. So Faraday's law, remember, is EMF is negative magnetic flux over, or the rate of change of the flux. So if we rewrite this equation, flux is equal to L times I. So an EMF is generated if we do the negative derivative of this. So negative derivative of L times I. Well, L, that's all these physical characteristics of how we built the solenoid. So it does not change with time. So the L comes out of the integral, or the, excuse me, the derivative, and then we're left with di dt. So EMF of a solenoid or of an inductor depends not on the current through it, but the rate of change of current through it. And I again want to go back to the capacitor and the resistor. The resistor is easy. The EMF across a resistor is I times R. The EMF across a capacitor, shame on me, I'm having to look this up so I get the ratio correct. For a capacitor, V is Q over C. So something relating to current or charge, because current is the derivative of charge. So we have charge, current, which is the derivative of charge, and the derivative of current. So the second derivative of charge, and that will come back in a little while. But the EMF of an inductor depends only on how fast the current is changing in the inductor. Well, if we have Faraday's law, we also need to apply Lenz's law to get a direction idea. Lenz's law. So you know from all of that coil and put a magnetic field through it and change the direction, and the coil doesn't want to change the direction, so point your thumb this way and you get flow clockwise or counterclockwise. Well, what it does with an inductor does not want the current to change. So if I equals 0, inductor tries to keep it 0. No current flowing. If the inductor is steady, excuse me, if the current is steady, the inductor tries to keep it going. So if you don't have any current flowing, the inductor is going to prevent current flow. If you have lots of current flowing and then you turn it off, the inductor is trying to keep it going. Or if you have a current flowing and you're trying to increase it, it's going to oppose that change. So again, oppose the change, resist the change, oppose the change in current. That's where negative di dt comes from. And we call this a back EMF. It's like an inductor is a little battery that does the opposite of what the rest of the circuit is doing. So if you already have current flowing and then you turn off the battery, you change off the switch, the inductor is actually going to keep it going for a while. If you initially connect a circuit, the inductor says, I don't want current, I'm not going to let you go this way. You may notice some similarities in what I'm saying here to what we did with capacitors. And we are going to put these circuit elements together in the next two units, or the next two assignments after this one. So there's one more thing we want to pull out of this, and that is energy. But to get energy, we're going to go back to electrical power. So electrical power, you know P equals IV. So for an inductor, the EMF is L, negative L di dt. So I'm going to drop the negative sign. So this is L di dt. Well, power, remember, is the rate of change, or it's how fast work is done, or the rate of change of energy being done. In this case, with an inductor, it is a form of potential energy. We call it magnetic potential. Well, yeah, we're going to call it magnetic potential energy. So we're going to replace power with the derivative of magnetic potential energy. And then I can drop my signs here so I can do Li di dt. So here's the first interesting thing. Notice that dt is on both sides, so we can actually get rid of it, because they're going to have the same behavior with respect to time. So what we're left with is this differential of energy, a little tiny bit of energy, is equal to inductance, current, and little tiny bit of the changing current. So we're going to integrate both sides. So if you integrate the derivative, you get back the original thing. On this side, we know L is a constant, but we need to integrate I di. So this is the same as x dx, or t dt. So this is x to the first power. We need to raise a power and divide by the new exponent, or t. So this is x squared over 2, or t squared over 2, or I squared over 2. And this is usually written so that it fits on one line. 1/2 Li squared. So the energy you store in an inductor is equal to 1/2 times the inductance times the current through the inductor at that moment squared. Remember, similar for a capacitor is 1/2 QV, or Q squared over 2C. So we actually have the same 1/2 power. Inductance and capacitance is just on the bottom because of the definitions. And then current squared, charge squared. I am going to make one little change. Your formula chart doesn't use UM for magnetic potential energy. It uses UL for energy stored in an inductor, capital L. Sorry about that. So we will put first resistors and inductors in circuits, and then later we're going to put inductors and capacitors in circuits. We're actually not going to put all three in the same circuit at the same time.